You ever wonder what really happens when you click add to cart on Amazon? I mean, how does a system like that handle millions of people doing that at the exact same time without ever going down? Well, today, we're going to crack open the original 2007 paper that started a revolution. We're talking about Dynamo, the legendary storage system that is the reason Amazon is quite literally always on.
All right, so here's how we're going to break this down. First, we'll get a handle on the insane scale problem Amazon was up against. Then, we'll dig into the radical, kind of controversial choice they made to be always on. After that, we'll get into the nuts and bolts of how Dynamo actually works, see how it was engineered to treat failure as normal, and finally, we'll look at the incredible legacy it left behind.
So, let's paint a picture. It's the mid-2000s. Amazon is growing at a speed that is just hard to even comprehend. And their infrastructure, which was built on pretty standard database technology, was starting to buckle. It was screaming under the pressure. I mean, just try to imagine a system running on tens of thousands of servers. At that kind of scale, things don't just sometimes break. They break all the time. A hard drive failing, a network switch dying. That wasn't a rare emergency. That was just Tuesday. It was a constant reality they had to deal with. And this quote, right from the paper itself, this is where you see the light bulb go off for them. It shows a complete 180 in their thinking. Instead of trying to prevent every single failure, they decided to just embrace it. They realized they had to build a system that expected to fail, a system that treated failure as just a normal, everyday event. And to really understand why, just think about the shopping cart. For a company like Amazon, the shopping cart is absolutely sacred. It cannot fail, ever. Because if you try to add something to your cart and you get an error message, Amazon doesn't just lose that one sale. They risk losing your trust, and that's a much bigger problem. So how in the world do you solve that? Well, faced with this massive shopping cart problem, they made a design choice that, honestly, it flew in the face of decades of conventional wisdom about how you're supposed to build databases. So you've got this fundamental tug of war in system design. On one side, you have strong consistency. This is what old school databases were all about. Every copy of the data is perfectly, instantly identical. But the price you pay is that if something breaks, the whole system might have to lock up and become unavailable to make sure no mistakes are made. On the other side, you've got high availability. This means the shop is always open. It's always ready for you to read or write data. The trade-off? Well, for a brief moment, the data you read might be just a little bit out of date. For Amazon and its shopping cart, the choice was a no-brainer. They had to be always on. And the core principle they adopted to make this happen is something called eventual consistency. It's a simple idea, but a really powerful one. It's a promise that says, look, if everyone just stops making changes for a second, all the copies of the data spread across the globe will, eventually, all catch up and look the same. It's a system that chooses to be available now and perfectly correct a little bit later. And this right here, this is the absolute crux of it. This was Dynamo's big, crazy, radical bet. They decided their system would be always writable. That means it would never reject your add to cart request. Never. Even if it seemed impossible or created a conflict. What they did instead was push all the hard, messy work of figuring out those conflicts away from the write and onto the read. Basically, we'll accept the data now and let the application sort out any mess later on. Okay, so how on earth did they actually build a system that could make a promise like that? Let's get into the mechanics. It wasn't one single piece of magic, but a really clever combination of a few different techniques that they wove together in a new way. So Dynamo's secret sauce really has three main ingredients. They use a technique called consistent hashing to figure out which server should store which piece of data. They use a flexible voting system or quorum to handle copying that data around. And they use a really cool tool called vector clocks to keep track of different versions of data when things get messy. Let's just zoom in on that quorum system for a second. The easiest way to think about it is like a committee vote. N is the total number of copies of your data out there, in this case 3. W for write is how many of those copies have to say, yep, got it, before a write is considered successful. And R for read is how many copies you need to get an answer from before you can return data to the user. The beauty here is that these numbers are tunable. Different services at Amazon could tweak these values to get the exact balance of performance, durability, and consistency that they needed. Okay, let's go back to our shopping cart because this is where it gets really cool. Imagine the worst case scenario. There's a network issue, and a user's app connects to a server that has a slightly stale, old version of their cart. Then they try to add a new item. A traditional database would see the mismatch and just reject it. Error. But Dynamo does something totally different. Instead of saying no, Dynamo says yes. It accepts the new item. So now, for a brief period of time, the system is holding two different, conflicting versions of reality. There's one version of the cart with just item A, and a new, branched version of history that has both item A and item B. This is where those vector clocks come in. They act like a sophisticated family tree for the data, letting Dynamo understand that these two versions have a shared past and where they diverged. And here's the beautiful part. This is the final step, called reconciliation. When the application asks for the shopping cart later, Dynamo doesn't try to solve the conflict itself. It just presents both versions to the application and says, here, you figure it out. And the application's business logic, which actually understands what a shopping cart is, it knows it's just a list you add things to, it simply merges the two versions together. The result? No data is ever lost. The add to cart is never forgotten. So handling conflicting data is one thing. But what happens when the servers themselves just, fall over or disappear from the network? Dynamo needed rock-solid ways to handle the constant chaos of the real world. One of its most elegant solutions for this is called hinted handoff. It's simple. Let's say a piece of data is supposed to be written to Node A, but Node A is down. Instead of failing, the system just sends that data to a healthy neighbor, say Node D, with a little note, a hint that says, hey, this actually belongs to Node A. Later, when Node A comes back to life, Node D sees it and just hands the data over. It's a completely seamless way to handle temporary server outages. And what about more permanent problems or silent data corruption? For that, Dynamo has a background process that's always running called anti-entropy. Its only job is to constantly compare replicas and fix any differences. Now, comparing huge amounts of data is slow, so it uses a brilliant data structure called a Merkle tree. Think of it like this. Instead of comparing two giant books word for word, you just compare their fingerprints. If the fingerprints match, the books are identical. If they don't, you drill down and compare the fingerprints of each chapter and then each page, until you find the exact piece of data that's different. It is an incredibly efficient way to keep everything in sync over the long run. So, after all of this brilliant, counterintuitive engineering, did it actually work? Did this huge bet on availability and eventual consistency actually pay off? Let's take a look at the impact. First up, performance. Amazon is obsessed with what they call the 99.9th percentile. In other words, the experience of the unluckiest 1 out of 1,000 customers. They found one optimization, just moving some logic from the server to the client, and look what it did. It cut the latency for those worst-case requests by more than half. That's a massive win for user experience. Okay, but what about all those messy data conflicts they decided to allow? Were they constantly cleaning things up? Well, this chart is just fascinating. In a 24-hour period, a staggering 99.94% of all requests saw just one clean, simple version of the data. Those conflicts they had engineered the whole system to handle, they were incredibly rare in the real world. Their big bet absolutely paid off. And Dynamo's influence was just massive. The ideas in that 2007 paper didn't just stay inside Amazon. They basically became the blueprint for the entire NoSQL database movement, inspiring hugely popular systems like Apache Cassandra and, of course, Amazon's own commercial product, DynamoDB, which powers a huge chunk of the internet today. And that really brings us to the core lesson here. The story of Dynamo is a story about trade-offs. To build a system that was always available, the engineers had to be willing to give up on the idea of perfect instant consistency. It forces us to ask a really fundamental question that goes way beyond software engineering. To achieve your single most important goal, to be always on, what are you willing to trade?